Our last section of chapter 3 discusses the applications of radians in regards to linear and angular speed. Linear speed is described to be, suppose that point P, here's point P, moves at a constant speed along a circle of radius r with center at 0. The measure of how fast the position of P is changing is the linear speed. So here's our first vocabulary word of the day, linear speed. If v represents linear speed, v for velocity, even though we're giving it no direction here, speed is going to be equal to distance divided by time, which makes sense to us if you've taken any sort of physics class. Rate is distance over time. For us, linear speed is equal to arc length divided by time. Since the distance around a circle will go around the pizza crust, that is the arc length. Okay, so we have arc length divided by time, which gives us the linear speed. If you want to make a note to yourself so later on you're not like, what does S stand for? Remember, S represents arc length, which is the pizza crust distance. The second type of measure we're going to look at today is angular speed. Angular speed is a little bit different. As point P, here's point P, and the figure moves along the circle, the ray OP is the terminal angle of BOP or POB. The measure of the angle changes as P moves along the circle, so it's going to get bigger and bigger and bigger and bigger. The measure of how fast angle POB is changing is called angular speed. So the measure of how fast an angle is changing as opposed to how fast we're moving around the circle, it's called angular speed. Angular speed, we use the Greek letter omega. Do not call this W.
So W?
It's omega. That is the Greek letter, the Greek lowercase letter omega. In uppercase, it actually does kind of look more like an O, but that is a lowercase omega. Omega is equal to the theta of the angle divided by time. So that is the angular speed omega. Here, theta is the measure of angle POB at time t. But be sure that you abide by this caution. As with earlier formulas in this chapter, theta must be measured in radians for this formula to work. It will not work in degrees. Therefore, omega is going to be expressed in radians per unit of time. So radians per minute, radians per second, radians per hour. That is how you measure angular speed. So let's make some conclusions here. This is going to be a good spot for you to look while you're doing your problems. This is going to be our quick little formula chart. We just wrote this down that angular speed is omega equal to theta over t. And that linear speed, the box above that, is simply arc length divided by time. But if we start to think about what we've already learned about arc length, there's actually a connection between linear and angular speed, which is pretty cool. The things we know about arc length, when we learned this a couple sections ago, is that arc length is actually radius times theta. S equal to R times theta. So if we substitute R times theta into the numerator here, we actually notice that we have theta over t. And what is theta over t equal to? Omega. So linear speed can actually be derived to be the radius times the angular speed omega. So you now have multiple variations of these formulas because they're related to each other by that arc length, by the radius and the theta. Do you want to see what this looks like in practice? Great. Keep these formulas in mind because we're going to be using them. But in this problem, example number 1, it says, suppose that point P is on a circle with radius 10 centimeters and ray OP is rotating with an angular speed of pi over 18 radians per second. So just because we want to make sure we understand what we were given in this problem, we were given that the radius is 10 centimeters and we were given that the angular speed, that's omega, is equal to pi over 18. Now we're going to leave them in terms of pi, because that's how it's given to us. Unless it specifically tells you to put a decimal version, you're most likely going to leave them in terms of pi. Part A says to find the angle generated by P in 6 seconds. Okay, we have now, for this particular problem, we have that time is equal to 6 seconds. That's a weird looking seconds. So we're going to have to do the following. We know that the 3 letters that we are given, R, T, and omega, are related by the following equation. Sort of. Omega is equal to theta over T. Because remember, it asks me to find the angle, which means I'm actually looking to solve this equation for theta. Because this is kind of touching onto some physics and touching onto some science, there's a general understanding in those classes that you derive formulas for what you're solving for first, plug things in second. So we're going to do the same thing because mathematically that makes a lot of sense to me. So if I wanted this theta to be all the way by itself, I'd have to get rid of the divide by t. How do you get rid of divide by t? Multiply by t on both sides. So I'm actually going to use the formula that theta is equal to omega times t. I've derived the formula so that it's equal to theta, what I'm searching for. Well, then you can just plug in things we know. For this situation, we know omega is pi over 18 radians per second, and we know that the time is 6 seconds. Now, let me write this in a different way, actually. That might make this a little bit clearer to you. If I have radians per second, and I'm multiplying by seconds, don't the seconds cancel each other out? Yeah. What am I left with? Radians. What are we searching for? Angle, which is measured in radians. Okay, so the units in these problems can and should cancel, 2 things that make sense. Can and should. Okay, so that means we're multiplying. We're going to go top times top, bottom times bottom. So 6 times pi is 6 pi. 18 times an invisible 1, because 6 is 6 over 1, is 18. That's 6 over 18 radians. Ooh, but we can reduce that number. What is 6 over 18 reduced to? 1/3. So this is pi over 3 radians. That is the angle that we have traveled through after 6 seconds moving at an angular speed of pi over 18 radians per second. I'm going to put this in like a little squiggly box so that I know this applies to the entire problem. That information right there. Because part B says to find the distance traveled by P along the circle in 6 seconds. So if we're looking for the distance traveled this time, distance traveled by P along the circle. Don't draw this, just watch for a second. Here's my circle. And if I'm wanting to figure out the distance traveled, what am I looking for? Arc length. Yay. We're looking for arc length. It's how much we've traveled around a circle. We're looking for the crust of that pizza. That is arc length. So we're looking for S. We need a formula that puts together the things we know. The things we know are the R, the omega now, because we were given R and omega. We also then found the angle at 6 seconds, so we know theta. Is there a formula that is solved for arc length, or that we can solve for arc length, that uses the formulas we know?
V equals S over T.
Yeah, V is equal to S over T. Let's start there. So V is equal to S over T. Remember, we're trying to solve for S. Okay. Let's first isolate S. How do you get S by itself? Times T. So it's going to be S equal to, this time, angular speed times T. Not angular speed, I'm so sorry. Linear speed times T. But do we know linear speed yet? No. So we have to change something here to make it something we can use. So question. What is another formula for V that we have written on our front paper?
It's radius omega.
R times omega times T.
Yay.
Okay, let's fill in what we know. We know the radius is how much? 10 centimeters. We were given that in the problem. What was omega? Pi over 18 radians per second. And what is our time? 6 seconds. Okay, we just need to multiply all these together, but let's figure out what units we're left with.
Okay.
Is their units going to cancel? Yeah, seconds are going to cancel out. One on top, one on bottom. They're going to be gone. Does anything else cancel? No, so it looks like I'm going to do centimeters times radians.
Okay.
Yes? But we are measuring, again, the distance traveled. When you measure a distance, would you measure in centimeters, radians?
No, centimeters.
Centimeters. Radians becomes unitless when you're multiplying by something else. If radians is there, we're measuring radians. But it's like basically overpowered by anything else that's in the numerator. So this is actually going to end up just being in centimeters, even though it would be centimeters radians, which is kind of weird. You can lose that unit when there's something else there, which feels like illegal math-wise, but it is what happens when you multiply radians times centimeters. So if we go ahead and do this math here, we'll multiply all of the numerators together, which is 6 times pi times 10. So that's 60 pi over 18. Gross. Can we make that look better?
I think so.
What is that reduced to? 10 over 3. 60 divided by 6 is 10. 18 divided by 6 is 3. So that's 10 pi over 3 centimeters. And since that's not normally how you answer questions, like if I measured something and I was like, this is 10 pi over 3 centimeters long, you'd be like, that's annoying. Can you tell me actually how many centimeters it is? This one will probably be asked to be given to a rounded decimal. So in your calculator, 10 pi over 3, can we type that in? Okay, shh. Let everybody type it in. Also, this music is too loud. 10 pi over 3. And then we'll round to 4 decimals. 10.4720 centimeters. Just depending on what you're asked for will mean if it asks you for an exact answer or to leave it in terms of pi, you'd give me 10 pi over 3 centimeters. But most likely you'll be asked to convert that into a number that like a regular person would know. Okay, guys. Part C, ask us to find the linear speed of p in centimeters per second. Now we technically kind of already started this because you guys knew that there was a substitution for linear speed. Linear speed is v, and based on the things that we know, v is going to be equal to r times omega, or s over t, because we now have the arc length and we have the time. But let's use r times omega here. We know that the radius is 10 centimeters, and we were given that the angular speed, the omega, is pi over 18. I should add units, radians per second. So question, what is going to be the units that are left over here when we actually do this multiplication? Centimeters per second, because the radians gets overpowered by anything else in the numerator. So this becomes 10 pi over 18 centimeters per second, which we can reduce to 5 pi over 9, I believe, centimeters per second. And in case it was asking for this with a rounded answer, what is that rounded to 4 decimals? .7453 centimeters per second. So again, just depending on what the question itself asks for, we'll let you know if you answer in terms of pi, exact answer, or a rounded number. So the gist here is that you're trying to figure out what you were given to know what you can fill in to then solve for that variable plug and chug. The last thing I always want you to do though is make sure your units are giving you what you should. Linear speed should be like meters per second. Well, we're doing centimeters per second, great. A distance traveled should be an actual distance, centimeters. An angle should give you radians. Now this becomes especially important to check your units when you're given a problem like example 2. It says a belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. So this one's easy. The question I'm going to ask is easy.
Okay, you sure?
R is equal to what?
6.
6. What letter did they give us here?
Oh, that's not one thing in the
Revolution.
V.
RMP. I mean RPM.
V.
Okay, RPM, revolutions per minute. But out of the letters from the beginning of our chapter, did they give me V, R, S, T, omega? We've used all of those today.
V.
It is not V, because V is a distance divided by time. It is omega. This is how many revolutions we have per unit of time. How many radians per unit of time we would have. So interesting here that we were given the omega of this problem, but in a kind of a weird way. This is omega, and this is the radius. The first question says to find the angular speed of the pulley. Great, 80 revolutions per minute, except it wants me to know this in radians per second. So we're going to throw back a little bit to a different kind of problem. I think we've done this before, and I could 1,000% be getting this confused with one of my other classes. If we have radians, 80 revolutions per 1 minute, and I want to change that to radians per second. Did we do this in this class, or am I thinking of a different one? Okay, so we're going to just do a whole bunch of conversions, correct? Let's start by getting it to the correct time. I don't want minutes, I want seconds. So what am I going to multiply the top and bottom by to switch it from calculating in minutes to calculating in seconds? 1 minute is 60 seconds. Because now the minutes cancel out and my units are revolutions per second. Great, but I want radians per second. So we need the revolutions to go away. How many radians are in 1 revolution?
2 pi.
So if we multiply that there are, in 1 revolution, there are 2 pi radians, the revolutions are going to cancel each other out. The only unit I have on top is radians. Radians sticks. The only unit I have on bottom is seconds. My calculations will then be in radians per second. Now, this is radians per second. We're most likely going to leave it in terms of pi. So we just have to deal with all the coefficients, which would mean I am doing 160 pi over 60 radians per second. Do you know where I got those numbers from?
Yeah.
80 times 2 is 160. Leave the pi. 60 seconds on the bottom. But then we need to reduce that fraction, obviously. So I noticed that they both end in 0. So I really can just reduce 16 over 6. What is 16 over 6 reduced to?
Something.
What goes into 6? What is your brain telling you goes into 16?
Oh, so it's 2 and then how much?
It's 8 over 3. 16 divided by 2 is 8. 6 divided by 2 is 3. So it's 8 pi over 3 radians per second. This one we probably, again, will leave in terms of pi. If the question happens to ask you for a decimal, you just type it in. Sound good?
Someone.
Then we can go a step further. The only information you were given at the beginning of this problem was that the radius was 6 centimeters and that we had an RPM of 80 revolutions per minute, that we have now created the angular speed in the correct units, radians per second. It should be in radians. So now we can actually answer the next question that says find the linear speed of the belt in centimeters per second. What letter is linear speed?
No.
Oh, no. V. Think like velocity for speed, linear speed, velocity. You can kind of start to think that way, even though they're technically a little bit different. Linear speed of the belt in centimeters per second. Okay, let's see if we end up with the correct units here. What's the formula we have for linear speed? Based on, that's correct. So S over T or R times W. Were we given S's and T's?
No.
Were we given R's and W's?
Yeah.
So that's the version we're going to want to use because that's the information we have. So we're going to do V equal to R times omega. I just said W because I listened to what you said. That is an omega. Don't call it a W. No, that's not its name. It's an omega. I know they look like W's. It's because I can't write Greek letters very well, but it is an omega. So sorry. Didn't mean to say that out loud. It should be omega. Okay. What is the radius in this situation?
6 centimeters.
6 centimeters. Good start since we wanted centimeters per second anyways. What did we just find to be the angular speed, omega?
8.5
Radians per second. And again, I'm going to write my units to where it actually does look like we have a tops and a bottom. If I were to multiply these numbers together, what would be my units?
Centimeters per second.
The radians kind of gets overpowered by the centimeters, so we're in centimeters per second, which is what the question wanted. We won't have to do any converting after this. You just multiply. So this would, be 48 pi over 3. But we can obviously reduce that. What's 48 over 3?
Number is?
It's actually a really nice looking number.
12.
No.
Am I close?
16.
It is 16. So we end up with actually this becoming 16 pi centimeters per second. But of course, if the police officer gets you on that radar gun and says, excuse me, so sorry, you're speeding at 16 pi centimeters per second, you'd be like, I don't know how much over the speed limit I was going. So we're probably going to want to write that one in decimal form. So 16 pi, that means that this pulley is moving linear speed at 50.2655 centimeters per second. Again, just depending on what is asked for, that's how you give the answer. Are we seeing kind of the pattern here? It's very helpful to leave your units showing so you know you're solving for the correct thing by the end. Last example for today. Example 3, finding linear speed and distance traveled by a satellite. So let's say we're measuring a satellite. It says the satellite is traveling in a circular orbit 1,600 kilometers above the surface of the Earth, and it takes 2 hours to make a full orbit, which is crazy fast. The radius of the Earth is approximately 6,400 kilometers. We have a figure here, so just to be sure you understand, the radius of the Earth, 6,400. The satellite is 1,600 kilometers beyond that. So question, what is the radius of the actual satellite compared to the Earth's core? Yeah, so the radius of the satellite would actually be 8,000 kilometers. Does everyone know how we got that number? You added them together because you have to get from the Earth's core all the way to the crust and then from the crust to the satellite. Okay. The question A says, approximate the linear speed of the satellite in kilometers per hour. To approximate the linear speed, the formula we're going to use here, I'm giving you a hint, is going to be r times omega. Were we given the radius of the satellite?
Yes.
Were we given the angular speed in radians per unit of time? Correct answer would be no. Question for you, what information were we given about any sort of speed here at all? It takes 2 hours to make one orbit, which means, just like the problem above this, it is 1 revolution in 2 hours. So before we even use the omega that we want for this linear speed, we have to convert it from revolutions per hour to radians per hour. Why can I leave it per hour, you ask? Because the question eventually wants kilometers per hour, so we can leave hour there. So what we're going to do is we're going to say, all right, our omega is actually going to be equal to whatever we get when we convert 1 revolution every 2 hours into radians.
Yeah.
So we only need one conversion here. How do you go from revolutions to radians?
2 pi.
2 pi radians in 1 revolution. Revolutions will cancel each other out. When you do this multiplication, what is omega? It's just pi. We have pi radians per hour. Okay, well now we have a useful omega. We need it to be in terms of radians per some unit of time that makes sense for the problem. A lot of times it's seconds, but in this case we're doing hours. So let's plug all of this stuff in. We know that the radius of the satellite is what?
8,000 kilometers.
8,000 kilometers. We know that the omega, the angular speed, is pi radians per hour. If I were to multiply this together, what units would I have?
Kilometers per hour.
Is that what I wanted?
Yeah.
Yes. So we double check our units before we do calculations and get upset. So we're going to do 8,000 times pi, which is easy if we're leaving it in terms of pi. That's just 8,000 pi kilometers per hour, but that's a weird looking speed, so we're going to go ahead and multiply that out. 8,000 times pi is 25,132.7412 kilometers per hour. Sorry, I got that all kind of bunched up there. Do we see how, again, this was kind of like example 3, part A. We had to do both parts that we did in example 2 for one question. Example 2 was showing you the idea of switching units before using omega. Example 3 is going to assume you know to switch units. So keep that in mind, that you may have to switch units before you use omega. Part B, though, says to approximate the distance the satellite travels in 4.5 hours. When we're talking about distance, what letter am I looking for?
Oh, no.
Distance. Like the crust of the pizza?
Oh, it's S.
Yeah, what does S stand for?
Arc length.
Arc length. We want to know how far it's gone around the circle, the distance around the circle, that's arc length. So we're looking for S. The formula I have that involves S is VO equal to S times T. But if we're solving this equation for S, what is the equation that we would use here? S equals to linear speed times time.
Yeah.
Do we have a linear speed?
Yeah.
We just found it, correct? Should I use the one that's in terms of pi or the rounded answer?
Pi.
The one in terms of pi, because we want to use an exact answer here. So we're going to plug in what we know, which is a linear speed of 8,000 pi kilometers per hour. And we're going to multiply that by 4.5 hours. If I multiply those units, what am I left with?
Kilometer.
Does that make sense for this question? Yes, because we're wanting a distance. That totally makes sense. So 8,000 times 4.5. I'm leaving the pi out of it for right now.
Oh.
Is what?
36,000.
36, one extra zero. 36,000 pi kilometers, which is a weird way to answer this question. So we're going to translate it back into decimals. So multiply 36,000 times pi. We should get 113,097.3355 kilometers, which is a lot of kilometers. That also makes sense because it's way up there in space. The game here is to use the two formulas we were given at the beginning of this section in different ways to answer these questions. Omega is always in radians per unit of time. That's going to be a conversion you're going to have to do from time to time. Okay, write your units down so you know you're solving for the correct thing. That's the best advice I can give you.